CFT. So it's been more than 2 years since I gave my last talk here. And I'll be talking about the project I was involved in recently. So as some of you maybe know, now I work in ICFO in Barcelona, but apparently I'm not yet used to the heat that much. I mean, weather in Poland. Okay. Whoa. Okay, it doesn't work. It doesn't work. So I guess maybe we can stop because the presentation wouldn't move. Okay, so like that. No.
So let's start the discussion.
Sorry. Yeah, sorry. Okay, so okay, that's my fault. But maybe let's stop. Sorry for inconvenience. Okay, because. All right. So this is a project I was involved in recently. So it's a joint work with a number of people from ICFO. So Remik, when the project was ongoing, was still in ICFO. Janek, Christian, and our bosses Tony and Maciek. So the project is roughly about I really apologize. Okay, the project is roughly about how random states are useful for quantum metrology. Okay, so before I move to the details, I just tell you the basics of what quantum metrology is. So imagine we have a quantum system which is formed from many distinguishable particles, qubits or spins, okay, that interact with the on every particle we have the same Hamiltonian acting. So like imagine a magnetic field that couples to every spin the same way, and the task that we have is to estimate the parameter phi, that is encoded on the state, on the state row that we prepare in the beginning, and then we let's say let it evolve for time phi, or there's some other, or that encodes this unitary evolution. Okay, so the most general strategy we can think of, is like we prepare the state. In the input we put it through this like machine that encodes this phase phi. Okay, we have this output, say rho phi, and then what we can do, we can measure our quantum system with arbitrary quantum measurement. Okay, we get some classical output x, and then our task, is to infer about the value of this parameter phi, conditioned on the value of the classical input output x that we got. Okay, and quantum metrology is about construction of pardon? Yeah.
We have to know first.
No. It's like.
You ask the question, what is phi?
No. So imagine you don't know precise value of magnetic field. Okay.
I'm not talking about the magnetic field. I'm talking that if I apply the U of phi, I have to know the U of phi.
No, I mean on the piece of paper, yes, but in the lab you don't, right? So
I don't know.
Right?
This is not clear. How do you apply?
How to apply if you don't know it?
You don't know
What's U? This U phi. So I assume that the evolution is of the form U phi, but it depends on some parameter phi that I don't know. Okay, so then I can. I mean, in what sense I can apply? I mean, on the piece of paper, I can always apply, but in the lab.
the parameter phi is identical in all the legs of this machine.
Yes. In the.
Is it realistic?
Well, I guess it's rough. I mean, it really depends on the situation, but in some cases it is. So okay. But can I just answer if the question is okay? So imagine you have like interferometer, right? And I mean, I'll be talking about this scenario later on. So you have photons that pass through interferometer.
So should I,
And
should
the-
I
the-
also
yeah.
interpret this as having this sequentially photons coming to the machine? Or is
No,
it
they come. Okay, they come in okay, in photons, it really like depends. I mean, if you, let's say, have like a bunch of photons that pass in the same time through this machine, then it's like equivalent to saying that they come in parallel. Okay, but yeah.
So you mean some highly occupied spots then?
For instance, yes. Right. So
From the point of view of a computer, is this a parallel architecture or sequential?
I guess this question is not relevant since it doesn't. I mean, there is no architecture. I mean, where do you have the computer here?
You wrote you draw certain number of boxes.
Yeah. So I
We don't know what is true, and we don't know how they
Fine.
arrange.
Fine. So the use are I apply them in parallel, but there is no computer whatsoever here. So I don't understand your question.
It's easy. If you send one photon and then wait 10 minutes and send another photon, it's very hard to argue that the state
Yes.
of the machinery remains the same.
Yes.
But if you send two photons in parallel, they have to be symmetrized. The wave function have to be symmetrized, so they just come really in parallel with the machine, right?
Yeah. Or I can imagine.
Simultaneously, not in parallel, simultaneously.
Sure, or I can imagine a situation when I have roughly, like fixed magnetic fields in some region of space, okay, and then I have spins that interact. I have some complicated system that has spin degrees of freedom, and they interact with this magnetic field. So, up to this approximation, the same Hamiltonian would be valid, okay.
Well, does that unifies one inside the box and the second is something that operator, which is the right-hand side focus, so this is the same?
No, it's the same. So it's like single part. So this U5 comes from.
You find the script which is put inside the box that
Yeah.
you have do you modify on some density matrix.
Well, here I didn't write any U5, right? I just wrote exponent of.
But is this
Yeah.
unified?
But it's the same if I...
No. Here it's like single particle one. I have small h coming from. Okay, and here I have capital H, and capital H is defined. So I guess it's.
Calligraphic U in the box.
Well, okay. Then there is a. Okay, it should be a calligraphic U here. Yeah, right. Right. Perfect.
But are those lowercase hi identical for?
Right. So maybe I will be. Actually, I wanted to be more specific. That's great. So, well, that's okay. So the specific system one can have in mind is many qubits or many spin 1/2 particles. Okay, and then so exemplary H would be sum of those HIs, and this HI is like identity on all J's different than I, right? And then I have, for instance, sigma Z acting on the ith factor in this tensor product. Okay? Yeah. So. Yeah. And all right. So let me maybe move forward. Right. So. Okay. So the task. Let me just repeat.
That are different for different components, yeah? For their identity.
Pardon? Sigma Z. In what sense they are the same? The Pauli matrix, or like one element of the algebra of SU2.
The same for all components.
In which sense? In what basis? Diagonal.
The usual basis.
In the computational basis, yes. That is correct. Right, and the task? Okay, so the general task, of All right. The general task of quantum. Okay. The general task of quantum metrology is to infer about the value of this phase phi as accurately as possible. Okay, and like the typical measure which is used to to quantify the quality of how good our estimator is its variance. So I assume that already I constructed somehow the estimator which is unbiased and some other technical conditions are satisfied, but you don't need to worry about them now. And what one can show in general that I really right. So that if I plug some separable states into my and in the input of my system, then this variance can be at most 1 over n. Okay.
The variance applied to
Variance of this estimator.
the phase is not a very good quantity. It depends where you are on the circle.
That is correct. That is a good question. So, but imagine that we already have a very good statistics. We gathered a lot of data. Then we, so it's this thing is valid if you, in a way, have already like quite good knowledge about the phase. This is a valid question, but on the other hand, this is like a standard thing that people use in this context anyway. Okay, but you can also think about like about the situation when this phi is not like it's not on the interval from 1.
As a usual index.
Yes.
So it is a phase.
Yes, in this case, this is a phase. But when you have gathered a lot of statistics, then you already almost don't have this problem that you mentioned, which is relevant. And then in the context that you, in the most general case, yes, some other measure of how good our estimator is should be applied. Yes, that is, for instance, like invariant under rotations on a circle. But this is like an introductory part. And okay.
Is this really 1?
Pardon?
1 over n?
Right, that is yeah, good. Okay, another relevant question. So, throughout the talk, I will care mostly about scaling with respect to n. So n would be a resource, and I will explain why in a second. Okay. So actually, this particular what one should have here in this denominator, there should be a difference of maximal and minimal eigenvalue of the local Hamiltonian. Okay?
This is simply an expression of the uncertainty relation between the phase and the number of quanta. Nothing more.
Well, but this.
You multiply it by n and you get n times.
But this is.
It's not 1. That appears in this expression.
I mean, so this variance is a variance.
2 pi times n.
Oh boy.
What do you call by variance?
So, okay, so
That is why I asked, what is the meaning?
okay, so variance, so I explained, so I have some estimation of this phase phi. I assume that this is like unbiased, so it's a classical object, okay, so constructed in classical statistics theory, okay, and I can compute its variance, okay, so, and then this variance is lower bounded by, 1 over n, but so this problem depends only on all parameters that I have in the problem is the number of particles and single particle Hamiltonian. Do you agree, sir?
Well, I would like to see the definition of the variance then.
Well, fine.
It's not the usual.
It's a usual one, so no. So okay, so I have okay, so
scaling with n, not the.
Yeah, but you guys wanted to have what is the variance, okay? So I have this rho phi, which is like a state on which this unitary acted, okay? And I measure some P of m mx. I'm defining, you wanted to have a definition of the quantity. So I have the probability distribution, and then I have like a estimator of this phi. Mx is a P of m. So a measurement, general.
There are many people.
Well, it's some P of m. Okay.
Somehow related to this problem.
But I would be very happy if I can like just. It's let's say at the moment some P of m.
I at least do not
Pardon?
understand. All of a
Yes.
sudden,
Yes.
there's a new notion, mx, well, there was somewhere maybe also.
It's the same one.
And yeah, that's right. Without any explanation, really. What is mx?
So mx is arbitrary measurement, okay? And then this inequality there is something like, okay, this variance is, okay, I have a bunch of variances that come from all estimators possible or measurements possible, okay? And then the statement is that for every, if I plug only separable states, then for every measurement, no matter what quantum strategy I decide to do, and no, yeah, then the variance of the estimator I construct would be lower bounded in this way, okay? All right, so but I can define the
classical result of probability of two independent probability distribution and have a variable which is the sum, then the variance of the sum is just.
I don't know what is called to understand here. So if you have a density matrix of some system, we can measure whatever you want. We can measure even the radius of the work with the special operator and it measures the radius of the work. Why not? Everything can be measured using this density operator. And then some measurements, whatever you want to perform on them. Okay?
In other words,
And this
mx
axis
arbitrary projection operator.
No.
It's a part of POVM. Maybe you have to explain to us all this. What's
But it's
POVM?
enough to say that it's any positive operator.
Yeah.
Yeah.
All the S law.
Yeah.
that is correct. I said arbitrary quantum measurement. I assume that quantum measurements,
Operator is positive.
Yeah.
a bunch of operators that sum up to. No, it's like for all x's I have that. So I have all the statistics. So can I maybe like try to explain? So I have.
Let him talk, otherwise nobody else, except of a few experts in the room, will be able to follow.
Well, okay. So I have statistics gathered. So I measure some fixed P of m at the moment. I don't care yet about which P of m. I can measure maybe some P of m. I gather statistics that depend on this value phi. Then I have some function which is a function of this output, classical output x. Okay, it is a and then if I assume that this x fluctuates according to this probability distribution, okay, which is conditioned on phi, on the true value of the parameter phi, then I get random variable that depends on the parameter phi. And I am in the realm of classical statistics, and the variance that I have in mind there is just a variance of this random variable.
So what is the formula? It's a number.
Fine. So fine, but I needed to define this first. So variance.
Fundamental question.
Yes.
What is the difference between x and mx? I suspect that x is just the abbreviation for mx.
No. No. X is a label of the output, and mx is a quantum mechanical operator that measures.
It's an operator which measures quantity x.
Yes.
I mean, that is what, I'm not sure it's correct, but that is my understanding. Therefore, if I measure f of x and phi, the results depend on x. And it is random.
So as I explained, this phi hat is a random variable. If I assume that this x
If you would
fluctuates,
write normal brackets as the average, everybody would be able to
No,
understand.
but we understand.
this is just standard variance.
We understand. Yes.
Okay.
Could you tell us also what's the estimate for the mean value of this fellow?
Well, at some point I said, so I assume that this estimator has the okay, it's unbiased, so the average value of this fellow is exactly phi. Okay, so actually here, yeah. So I assume that this is the case. I have unbiased estimator. Okay. This is, yeah.
If you can estimate, then who cares about the variance? Who cares?
No. I mean, so imagine I have an estimator that gives, like, in expectation value the same, the right quantity, but its variance is very huge. Some classical. So then I have very huge.
Variance in this case.
Pardon? So
we need this value.
I
So-
think I understand.
so variance is the quality of this estimator. Different estimators can have different variances, even if they are unbiased.
Estimator is fixed, it's fine.
No. Random estimator is the function from the output space to, to real number in this case. Okay? And then if I assume that this guy x here fluctuates according to this probability distribution that depends on this phi, yeah.
No. The question is that this is some. We take a variable m of x, which provides us with the number x, which somehow depends on the value of phi. But we want from many measurements of the variable x to infer the information about the phi.
Yes.
And so
Yes.
we get this collection of what is the phi with effect, right? It's not an operator, it's a collection of numbers, right?
No, phi hat this is estimator. So this is some.
Well, never mind. There is a certain collection of results from
Okay.
Estimator is not a collection.
No,
Yes. So statistics is one thing, estimator is another thing. All right. So I can have. So I guess we agree that in the classical statistics we can have estimators that are unbiased. Okay, but some of them would have very small variance. Some of them would have huge variance. Okay. And the task that we are faced with is, okay, we have this system that I explained in the first slide. So I have my quantum system, I have n particles, I have my Hamiltonian there, capital H. So all parameters that I have here is n, and the single particle Hamiltonian H. Okay, so all the results I should somehow have should depend only on those parameters. Okay, so just coming back to your question about this denominator here. Okay, so this variance here is the variance for like all possible unbiased estimators I can have. They depend on quantum strategies. Okay, I can have different estimators like themselves. Okay, and so I have a whole bunch of those guys. But then the claim is like if I input separable state in the input, then no matter what I do, I would be greater or equal than 1 over n.
Is this a mathematical inequality?
Yes.
Or this is just
This is a mathematical inequality
can be proved?
that can be proved. It has been proven by Caves and Bronstein, I guess in '96 or maybe even earlier, actually. Yeah.
So in other words, if I take gross separable and whatever estimator I will use,
Yes.
the theorem says that whatever estimator is used to estimate
Yes.
the quantity phi for
Yes.
rho which are separable, then the variance for that estimator
Yes.
cannot be less than 1 over n.
Exactly.
And that is a very simple statement.
Yes.
Of a classical probability
Exactly.
calculus.
Exactly. So just coming back to your question, I mentioned that the problem depends on single particle Hamiltonian. Okay, and here actually in the denominator I should have the difference of the minimum and maximal eigenvalues squared. But I just for the case of for the sake.
Mathematically true. If there is
Okay, this is mathematically true if if this single particle Hamiltonian is 1/2 sigma z, okay? Then this is mathematically true. Then there would be some not correction, some expression that depends only on the single particle Hamiltonian. But throughout the rest of the talk, for the sake of simplicity and clarity, I will just skip this part, because I will treat this n, as I will explain in a second, as a, let's say, main resource that we have. So,
And what is the state for which this is an equality?
what is, well, okay.
Is it saturated?
Yes. So one can show, yeah. So the state is for this particular Hamiltonian, right? You're asking. Yeah. So then this is like equal superposition of 0 and 1, and then the same like the same state in every Hilbert space, a single particle Hilbert space. All right. But then the crucial part comes that if you, in quantum mechanics, one can also put entangled states.
Is that
yes.
do I understand this expression correctly? If the Hamiltonian is 1/2 sigma of z,
Yes.
then I can think about it as a correction of a spin 1/2.
Precisely. And this is the
field, right?
precise. This is very good intuition.
Is this correct that this state is a paramagnetic? So if I have the correction of a spins, right?
Yes.
And one of them can point this way, the other one the opposite direction.
Yes.
Then I would call it paramagnetic if no chosen direction exists.
But paramagnetic somehow refers to some I don't know, thermodynamical quantities. No.
The collection of spins,
Yes.
where there is, roughly speaking, equal number of spins pointing north and south.
Yes, but this is a quantum state, right? So
Yeah, I get the state of sigma x.
yes.
So the sigma is, that's
I presume that it would
Yeah, so it's not. It's a quantum state, not just superposition, not just
they are not spin 1/2.
not states like that. No, it's a very different state. There's coherence in single particle Hilbert space. So,
I
but
guess another
yes.
example would be if it's an eigenstate of sigma y. Because I just wanted to
Wait, no. This. So actually, here you can have every phase, any phase. Yes, any phase would be yes.
But then you can cover the whole circle.
Yes. So that's true. This quantity is invariant.
Variable field, so
Right. Okay, and then. That's very the beginning. Yeah. So now the crucial part is that, okay, in quantum mechanics we can input entangled states a priori, right, to our quantum system. Okay, and then maybe there is some gain coming from that, and actually this is the case. Okay, one can show that if one plugs some particular entangled states to the system, much greater precision can be achieved in terms of n.
But we thought you
Yeah.
were heading towards telling us that this so-called standard quantum limit can be saturated, and now you are talking about.
No, I mean for some particle states. No, I mean it can be saturated for some particular product states. Yes. So this is what I said, and then in quantum mechanics we don't have only product or separable states. We have also entangled states. So then.
I don't understand, because if variance is greater than 1/n, then it's obviously greater than 1/n squared if n is greater.
Yes, but okay, but the claim is this inequality can be saturated. Okay, so for some particular.
The problem is that it cannot be smaller.
Yeah.
Yes.
1/n.
Yes. So the limit here, this is at.
1/n. If you plug the entangled states, you can have this 1/n squared, which is better.
Yes.
Because it's sharper. The variance is smaller.
Yes.
Well, there is some problem that I have, because if this is a mathematical inequality that can be saturated, how can you go below?
because for separable states.
I was explaining, and
But entangled are a special case of
No.
No.
Not separable.
Entangled are not separated.
But entangled
Wow.
would be a little bit entangled.
Okay.
yes.
Yes.
then I
But
don't
then the
see-
assumptions of the first theorem are not
It's
satisfied.
not fulfilled.
And then this equation changes. So in
Yes.
general case, the theorem says 1 over n squared. But in
Yes.
particular case, if you have separable states, there's another state.
Yes,
1 over n.
and separable states just from a tiny bit of my Hilbert space or the states that I have, right?
So let's continue.
Yeah, that's very okay. Okay, and another slide. Oh, great. Third. So now it's the thing is okay. I will be just stating the let's say the facts without proving them because I need to like go to the results that we actually got. So it turns out that the quantity that is responsible for this behavior, okay, is so-called quantum Fisher information, which is a function of the state and the Hamiltonian that encodes this phase. And okay, it's like a theorem that whenever you have some state rho, okay, then this inequality holds. So whatever estimator you can come up with, whatever you measure, your variance would be at most 1 over quantum Fisher information, okay? So then the bigger, moreover, this bound is saturable in a sense that one can actually construct estimators that give this this scaling. So then so then different states, different quantum states have different quality for metrology. The bigger quantum Fisher is, the better. All right, and it's maybe not so relevant how this function is, let's say, defined. It has some nice properties. So I just maybe mentioned that for pure states, that turns out to be just the variance of the Hamiltonian. All right, up to some factor 4, which is not that relevant. Okay, and moreover, okay, it's like this quantity is like non-negative, goes from 0 to this n squared times some constant, which is also not relevant for the problem. Okay, so we have this picture that different states have different usefulness for metrology. Great, and let me maybe give just a glance of the state, which is like let's say in this particular case with this Hamiltonian, which is the best. So this is so-called G8Z state or Nun state. So I just have this kind of superposition of all zeros and all ones. Okay, so this is a highly entangled state. All right, and the whole project that we have is to understand which qualitatively and quantitatively what states are good, what states are bad for metrology. Great, and is it in particular we will ask the question whether the metrological usefulness of quantum states is generic in the set of all quantum states. All right, so let me just give one more, like a tiny computation. So it may seem that this that the metrological usefulness is very fragile property of quantum states, because imagine I just lost one particle, then I take the state, I need to trace one particle from it, and then I end up with a separable state. Okay, so the state will be 1/2 0 and -1 plus 1/2 all ones. Okay, and then this state is clearly separable state. So so the quantum Fisher already drops for it to n, from n squared to n upon just the event when one particle is lost. So the task of the project that we have, is to study, limit of large particles, and we say, imagine this godlike being that checks different states from the all possible variety of quantum states, and we ask, is this metrological usefulness generic or not, okay, in the set of those states. And okay, whoa, this is actually not the right presentation. All right, so I really apologize. So the answer is the answer is, okay, so if I take random states from the space of all particles, okay, distinguishable ones, then generically, even though those states are very entangled, okay, generically I don't get this quantum advantage. I don't get this n² like behavior. But I just get typically behavior like this variance case like 1/n. Whereas if I take just symmetric or bosonic subspace of this Hilbert space and I look for random states there, typically I will get scaling like n². Moreover, this behavior would be robust to particle losses in this sense, and in a sense it will be also possible to measure it, to access this variance, access this usefulness in realistic scenarios. All right, so this is like, since I already passed the half of my talk, so this is like the main.
This question is asked under the condition that we fix H, because Hamiltonian.
Yes, obviously, yeah.
We concentrate on this very Hamiltonian.
Yes.
And then ask for the question.
Yes, I mean, we have a bunch of results, but let's think, yeah, that we fix a Hamiltonian. All right. So,
Where is it?
so actually, so the project started in Benasque. There is a very nice, like, sort of resort in Pyrenees. Okay, and they held this amazing quantum information conference every 2 years. And yeah, so first I will give like introduction to the concentration of measure, which is the main technical use I'm using. So it will be more like a bit like technical part of my talk. So we'll climb some mountain, but then it will be just physics and pleasure and getting the.
This is close to Medical Hospital.
No, this is Aneto. This is Aneto. Yes.
Medical Hospital.
No. This is a valley in a valley of Aneto. All right. So what is? Okay, I mentioned about typicality and about like average, typical behavior of quantum states. So, but I have to specify ensemble that I'm studying. So, I will be studying a set of isospectral density matrices. All right. So this is a generalization of the set of pure states. So imagine I take some state with fixed spectrum on a P1 up to PD, and I act on it with all possible unitaries. In this way, I get all states that have the same spectrum, and I will be studying this ensemble of density matrices. So as I change the spectrum, I can move from the set of from all pure states to the maximally mixed state. So in this way, I would model the noise that can affect the system in some way. All right, and so the main technical tool we are using is concentration of measure phenomenon. I don't have too much time to explain it, but roughly speaking, this is a phenomena when you have a high-dimensional manifold, okay, or high-dimensional space, and you have like a regular function defined on it. Also, you have some probability measure. Then it happens in many cases that one can derive very efficient large deviation inequalities. So for typical values, if I have some random variable defined on the space, so for instance, I don't know, momentum or whatever, and some function, then with high probability, this function would take values very close to the average value, okay, with respect to this measure. And okay, a high-dimensional sphere is one example. Also, this kind of inequality occurs for special unitary group and other manifolds. And throughout the talk, I will resign from technical statements. I will just focus on qualitative statements. So if you have some well-behaved function of SUH, then the probability that some random variables differs from the average value, okay, a lot, I mean, differs greatly. This is a really qualitative statement. Then this probability would be very, very small in terms of, say, the dimension of the Hilbert space. So I'm very qualitative here, but yeah, I want to stick to this level. And let me just mention that, okay, this technique was used in many places in quantum information and statistical mechanics as well. And one exemplary statement I want to focus on is the case of random pure states on bipartite system. So imagine I have random state on bipartite system, like uniformly distributed, and then I increase the dimension of the second Hilbert space. Then with high probability, it turns out that the reduced state on the Alice part on the first system is very close to the maximally mixed state. Okay?
But if
Yes?
this is only a probabilistic statement, then cannot be given as an inequality.
Yes, it's almost sure.
No, I mean it's like with probability which is smaller than something.
Say almost surely, so this means that
Yes.
it's not always surely, but the probability goes to 1.
Yes. Yes.
When did you measure it?
Yes. Yes. So this is like the intuition, like when we have huge like Hilbert space and we are studying entanglement of pure states there, they are typically very entangled. All right? And then the question is how metrological properties transfer, behave in this kind of limits. This is like our project, I mean, at least part of the project. So, okay, we already passed some technical difficulties, so it's a netto still. All right, and this is like, hopefully last technical slide that I have, then I will pass just results. So this is like the outline of all the technical things that we do in this project. So our function of interest is, okay, this quantum Fisher information or some quantity derived from it, like when I lose particles or something. So I have this, quantum Fisher information, and then what we do, we first have to, okay, quantify how this function fluctuates, or how this function changes when I change the argument a bit. So I have to upper bound Lipschitz constant of this function. So this is some quantity some feature of the function that measures how fast it changes when I change the argument. Then I need to compute or bound the expectation value of this function on the ensemble of my states. And then the catch here is that those unitaries here can be either unitaries that act on the whole Hilbert space or just on the symmetric subspace of it. Okay, so depending what I assume, I will get different results. Okay, and I will be using, for convenience, the capital theta notation. So I would say that function f of x is of the same order of g of x, even only if in the limit of large x's, up to some multiplicative constants, they have the same behavior. Okay, so that was the technical part. We'll reach the peak of the mountain, and then we can, I can finally, tell you about the results that we have. So first result concerns distinguishable particles. Okay, there is this notion. All right. We also have local unitary optimization. So let me maybe say. It's not true that all entangled states give you, let's say, good Fisher information. So imagine a decay state. Okay, this state is an eigenstate of this Hamiltonian, so it's not useful. Okay, for metrology, because it would not be affected by this evolution. But before I put it to my protocol, if I rotate it a bit so that it becomes a decay state in the X basis, it might be useful. So I want to take into account also possibility for this optimization before I enter the protocol. And don't focus maybe of this on like specific forms of those equations, but the qualitative state method is the following. So if I fix single particle Hamiltonian local dimension, okay, then even if I allow for local unitary optimization, with high probability, this quantum Fisher information would be smaller, would be of order would be of order n, so not n squared. Okay. So even if I take higher distributed random states, they typically, even though they're highly entangled, they have just linear scaling of quantum Fisher information. So this is a rather in the limit of large n. So this is a rather pessimistic result because, okay, entanglement doesn't help that much. But then we thought, okay, let's move. Actually, that was Remig's suggestion. Let's move to symmetric states. Okay, so right. So I have symmetric subspace of this space with respect to permutation of particles. And for instance, this state GHZ is in this symmetric subspace, or decay states are in this space. So how good are states from this symmetric subspace? And somehow surprisingly, we found that even if you don't do this local unitary hocus pocus, then with high probability you typically get Heisenberg scaling, okay? As the number of particles grows. Okay, so the message is, if I take distinguishable particles, typically I'm not useful, but if I take symmetric states that can even be somehow mixed, okay, so isospectral states that are not too mixed still would give me good scaling, all right? But I want to stress that I'm just giving qualitative statements. For quantitative ones, please ask me after the talk, okay? Because it's like we have plenty of results still here, okay? Well, all right, and okay, just as an illustration, so even if I allow for even if I decrease the purity of my state, then the scaling would still be good if this noise level is not too big. So I mix here hard distributed pure state with some maximally mixed state on my symmetric subspace, and the thing is,
So there is something.
Yes?
Representation.
Yes.
Psi is a state vector or what?
psi is a state, is a projector.
Projector, but not.
So should be bracket. Can you bracket?
The brackets are
Yeah, so in a standard notation that would be, yes. Yeah, so this is a density matrix, yes. Yeah, so even if you add quite a lot of noise, so like 1 over n squared noise or 1 over n, sorry, if you add noise, strength of the noise would be like 1 minus, okay, if it's not very close to 1, to the maximal strength, then still you get Heisenberg scaling. This is all I want to say about this slide. And okay, now let me move to the losses of particles. So you have seen that if I take this guy, which is super useful, it may seem, I just lose 1 particle, and then we end up with separable states. So is this
Lose means measure or just
lose? Okay, lose in this case mean we model it by taking a partial trace.
Yeah.
All right. So there are different model of losses, but let me focus for the time being on this particular one. So the question is this behavior generic? Okay. So how we model those losses? So okay, I will just focus on one of the equivalent ways to explain. So I have this state in the input. Okay, I encode this phase. Then imagine I can just measure n minus k out of n particles, and k is some fixed number. Okay, and then I can infer about the value of my phase phi just from measurements on the subset of particles. Okay, so the technical difficulty that we have now is that the ensemble of states that you get in this way, if this input state is, say, pure state on symmetric on symmetric subspace, the partial trace of the state gives you an ensemble of quantum states which is not well studied. Okay, so we couldn't like just apply take averages directly. We had to resort to some bounds, but still the result that we got is quite nice, I think. So again, don't look that much on the expression. So qualitatively, what is going on is that if you fix the number of particles that you lose and measure the usefulness of quantum states that you got in this way, then typical symmetric states are still quite useful. Okay, so still can give you Heisenberg scaling for fixed.
Does not depend on K?
So this is a very like this is this is for fixed one, which I silently assume now that is yes, that is much smaller than n. We have stronger statements. Okay, just for the sake of simplicity, I didn't write them yet. But then, even if you allow k to grow somehow with n, then you can still get advantage, provided this growth is not too big. Okay, so this is It's some detail, but the dimension of the single particle Hilbert space enters here. But for fixed, the simplest statement is that for fixed k and n going to infinity, you still are useful. Okay. All right, and now, so how much time do I have? At least 10 minutes, because I started, I guess, a bit late, but all right. All right, so now maybe I'll come back a bit to this discussion, because the thing is, this methodological usefulness of quantum states, in general, one has to input state, one has to adjust the measurement in the output, the things that you measure. So in order to get this high sensitivity to the phase fluctuations, you need to adjust this P of M. Okay, so it would be good to have a statement that for fixed P of M that you measure, you still get advantage. All right, because I prop all random states, I get huge Fisher, but to every single one of them, I have to pick the right P of M. All right, and then the question is, can I get something nice for fixed P of M? So, the quantity that is responsible for the quality of estimator in this case is the classical Fisher information, which is just a function of the outcome probabilities for fixed P of M, for fixed measurement that you choose. All right. So the question is, can we choose those MXs such that we get good scaling of this classical Fisher information? So, in other words, can we have good advantage in metrology even if we don't adjust the measurements to the input states? And then the answer is somehow I don't have that much time, but the answer is yes. So we study particular interferometric setup. So I have two bosonic modes, that I can model the corresponding Hilbert space. When I have n particles, I can model a symmetric subspace of this many qubit Hilbert space. I have the same phase encoding, and then I have standard 50-50 beam splitter, and I measure the particle number of particles in the output ports. All right, and then, not going into details, if I here in the input put hard distributed pure symmetric states, then with high probability I will get scaling still n squared for fixed P of m, for this particular P of m, which is okay, given pictorially here. I don't have, unfortunately, that much time to talk about the details. Right, so, and the question is, okay, then the question is, okay, it's very nice, we have those symmetric, random symmetric states, but how those states do not occur in nature generally. Okay, so can we maybe apply some physical process to construct states that would have properties similar to those high random distributed symmetric states? And the way we approach it, we construct the sequence. Okay, first the gate set, the set of gates that is universal in the symmetric qubits, in the space symmetric subspace of multi-qubit space. Okay, so this construction is somehow motivated by experiments, in a sense that we take some elements from linear optics, something which is in this setting natural, and we just supplement it by some cross-Kerr interaction. Okay, it's not okay. So imagine you have two optical modes and you have some nonlinear medium, then you might, in some approximation, get this kind of interaction. And then we construct, I'll be just qualitative now. You construct random circuits formed from those gates. So this is a bunch of your linear optics transformations. You have this particular gate, then you arrange k of them at random, and it's actually a very beautiful field of mathematics. It's possible to prove that as the depth of your circuit increases, you can mimic states that are hard distributed in some sense. So I don't have too much time to explain it, but unfortunately, the rate of convergence cannot be addressed analytically, so we resort, in this case, to numerics. And here you have, let's say, plots of how average Fisher information behaves with the, let's say, quantum and classical one in this setup, how it behaves as a function of the depth of this random circuit. So you indeed see the convergence to the average values that correspond to hard distributed random states. Moreover, the depth of the circuit is not that, okay, this is, as far as I remember, for 100 particles, so you need roughly, I don't know, 20 or 30 gates.
So we have two horizontal lines because
so this corresponds to quantum Fisher of different colors here come from different initial states. So I can start now here I start from J8Z state. So then I mix it a bit, but I end up with something which behaves like average state. I can also set from some product, a very stupid state. Then I would increase.
second line.
To classical Fisher. Classical Fisher for this particular interferometric setup. Okay? No, classical for both. So actually here you have the limit for separables, standard quantum limit, and then here you have the Heisenberg limit. But the scaling is still good. Yeah, in terms of n. All right, so here is how those variances behave as a function of n. That's the summary. So hopefully I managed to the result, the main results are as follows. So if I take uniformly distributed states from the set of all pure states on distinguishable particles, I don't get good scaling, even though the states are very entangled. I get so-called standard quantum limit. But if I move to symmetric states, then the behavior is very nice. Typically, we achieve Heisenberg scaling. Moreover, this behavior is robust to the loss of particles and to noise somehow. We also demonstrated that standard interferometric setup suffices to reveal this metrological usefulness of typical bosonic states. We also constructed a set of gates that are universal for the bosonic subspace of the full Hilbert space, and we showed that numerically, unfortunately, only that short random circuits generate states that mimic properties of hard distributed random states. The more details you can see in the paper. Whoops. Okay. And in the end, since we have the Children's Day, I think that scientists are like like kids. So I wish you very much to keep on having this curiosity and interest in solving problems in physics, mathematics, and so on. And I conclude with the list of open problems.
One of the key results was to show the difference between generic states and those states which live in symmetric subspace.
Yes.
And this somehow relies to the fact that it is conditioned on the choice of Hamilton. Your Hamiltonian is symmetric, isn't it?
That is correct, yeah.
So you think that your result somehow crucially depends on the choice of the Hamiltonian? If you choose it.
That's true. That's true. So Karol, what Karol means, what you mean is that it preserves the subspace, for instance, and it's invariant under the action of permutation group. Yes.
Okay, what do you mean by symmetric subspace?
Symmetric subspace, I don't know what is Hamiltonian.
That means these particles are indistinguishable then with Hamiltonian matrices.
Okay, but somehow, what changes if you change your assumptions?
Sure.
Distinguishable, otherwise there were no other parts.
Sure. So what I can say that even if you allow for some interaction terms here, if you, for instance, if you would have interaction like that, all particles interact with each other, okay, or you have like all k-body interactions possible, then okay, one can derive also analogous Heisenberg bounds or bounds on Fisher information, and then one can show that for distinguishable particles, you will still get not good scaling. Okay, it comes from the fact that marginals of multi-qubit or multi-qubit states to few particles are very mixed. And okay, if you trace out the derivation, this is like the core reason for that. I would suspect that symmetric subspace would give something good for these particles. Can I also like comment a bit on the basis of your question? So actually the same kind of behavior happens not only in the same kind of good behavior happens not only for the symmetric subspace, but in this space, if you decompose it onto irreducible representations of SU2, you have bunch of representations, right? And the thing is, if you take representations that have topological momentum greater than some threshold value, then one can still show that the scaling is good, provided that this the value that you take is not too small. Okay, so in that sense, also some other subspaces are good. Okay, right.